Hi, my name is Daniel. I'm a current sophomore at Chadwick International, and I'm here today to explain what Ampere's law is and how it's applied in a real-life situation. So have you ever wondered how a DC motor works? I mean, it kind of works like magic. You apply electricity and it starts rotating like nothing. Well, for that purpose, I have built a miniaturized DC motor over here, and I made it using this device. We call this a solenoid. It's basically a loop of copper wirings in a circular fashion, and I have stick these two ends out and stripped the ends so that I could expose it to these two paper clips over here. And this is powered by a 9-volt battery, which is also connected by a copper wire. And we have a pneumatic magnets in between the two paper clips, and we'll explain why that is in a moment. So if we carefully place the solenoid, with a slight touch, you'll see that it turns. To really have an intuitive sense of how this works, we'll have to go back to special relativity. Consider a copper wire with equal numbers of electrons and protons. We now set a positive charge moving at velocity v to the right. Because the wire has a net charge of 0, no coulombic forces will act between the wire and the charge. Now, even with current setting the electrons in motion with velocity v to the right, by the way, the velocity of the electrons do not have to be the same with the positive charges. We just had it for the sake of convenience. Anyways, even with current, the net charge in the wire intuitively seems to be constant, so no coulombic forces will still act. However, it is an observed fact that moving charges next to a current-carrying wire experiences a magnetic force. So, what's going on? Well, in special relativity, we learned that moving things appear to be contracted along their direction of motion. Although this is extremely vague, the derivation of length contraction cannot be dealt in this video because that will lead into a whole series. But hey, if we look at the positive charges in the wire in the perspective of the positive charge moving with the velocity v, along with the electrons, what we'll see is that the positive charges, the protons, will begin to move to the left with velocity v, because that is their relative velocity. So in reality, when viewing the protons in the wire from the perspective, from the frame of the positive charges will contract. So in reality, in the frame of the positive charge over here, the charge density of the protons in the wire will appear to be greater than the charge density of the electrons. So in the frame of the positive charge, the wire will appear to be more positive than negative. So the positive charge over here will begin to have a coulombic force directed downwards. It will repel the charge away from the wire. So if you were to look at this from a stationary observer, the moving positive charge will not only move to the right with velocity v, but it will also be repelled downwards with a vertical component because of the greater charge density of the protons in the wire. So this other repelling force that this positive charge experiences as it moves is the magnetic force. Now we get to the conclusion that a current induces a magnetic field. In a straight wire like this, if currents were to go in the upwards direction, we use the right-hand rule to determine the direction and the orientation of the magnetic field. So if we have the current facing upwards, going upwards, a magnetic field will form circularly around the straight wire with the right-hand rule. So it will go in the counterclockwise direction. However, in the case of a solenoid where each layer is stacked up on each other, the magnetic field produced by a single line, the single layer on the solenoid, will stack up on each other. It will superimpose. That's why we get a stronger magnetic field out of a solenoid rather than a single wire. So if I were to loop the solenoid a bit more loose like this, and connect it to a battery source through these two ends, sending a current from the blue end to the white end, what we would have to do to determine its magnetic field orientation is to use a modified version of the right-hand rule. Before, in the single wire case, we had our thumbs pointing in the direction of the current, and we had our four fingers directing where the magnetic field is formed. But in the case of a solenoid, if current were to flow up, go down, go up, and go down, When you view from the camera, current will be flowing in this way. It will climb up, go down, will rotate, and climb up, go down. So we will have our fingers, 4 fingers now represent where the current is flowing, the direction the current is flowing through. And our thumb will be pointing where the magnetic field lines are set out. And the other end would then be where the magnetic fields enter again. So, like that. You might wonder why magnetic fields can't never be produced and just spread out infinitely. It always has to come back like on a bar magnet, like as what you see on the screen. And that's another law in electromagnetism, and it deserves another video. It basically says that a magnetic monopole can't exist, that a single source or a single sink cannot exist in free space. Since on a bar magnet, we defined the north pole as the pole through which magnetic field lines are produced, and the south pole is the pole through which magnetic field lines are retrieved. On this setup we had before, magnetic field lines will point outward through my fingertip. So my fingertip will be like the north pole and it will be retrieved by the knuckle. So my knuckle will be like the south. So if we look at the DC motor setup we had before, if we send a current through this paperclip and exit out through this paperclip, as the current travels through the solenoid, it will create a electromagnet, a temporary magnet. And the magnetic fields that result from this solenoid will interact with the magnetic fields produced from this neodymium magnet, this permanent magnet, and it will cause the solenoid to rotate. It's as if we put 2 bar magnets together. It repels or it attracts. If we look at the setup again, this solenoid, as it turns, it interacts with this neodymium magnet to repeat the process of being attracted and being repelled. That's why it's able to rotate over and over again. Just as we see how current can induce a magnetic field, a changing magnetic field can also induce a current. In fact, this is how induction cookers work, as we see in the following video. We can see here that a changing magnetic field produced by the induction cookers can turn a LED on. Just to sum this video up, Ampere's law, along with this phenomenon, and 2 other phenomena, compose the theory or study of electromagnetism. And the 4 laws that dictate electromagnetism are called the 4 Maxwell equations, and they deserve a whole video on its own. Until we do that, it was Daniel Lee, and thank you so much for watching.